to have Ovidiu Savin delivering the third lecture on the Monge-Ampère equation.
Okay. Okay, thank you. So, I will continue talking about the Monge-Ampère equation. So what we saw so far, that the Monge-Ampère equation, I mean, affine invariance plays a crucial role in the Monge-Ampère equation because it leaves the determinant invariant. And then last time we talked about the Dirichlet problem, but also an interior estimate due to Pogorelov, which said that as long as the function is 0 on the boundary of some domain, actually one can bound and solves determinants. So let me recall Pogorelov estimate, which says if I look at the determinant of this square of u equal to f, which is a nice function, C2 f bounded above and below, and u equal to 0 on the boundary of the domain, then u is very nice. Let's say u has 3 derivatives in omega with bounds, as long as I stay away from the boundary. Yeah, but there is a second condition that we need to assume that u has to be 0 on the boundary, or u, because the equation is left invariant if we add linear functions, is the same to assume that u is a linear function on the boundary of some domain. Then inside we have some estimates on the second derivatives. And there are some examples also. I mean, there is an example due to Pogorelov which says that this is not in general true without the second assumption that u is 0 on the boundary of omega. So there is this example, let me remind you, of some singular solution that can be singular on a line that the second derivative can tend to infinity on that line. So for that reason, it is important to define places where I can write these estimates, and these are called sections. So whenever I have the graph of a function u that I think solves some Monge-Ampère equation, I would like to be in the situation of the Pogorelov estimate. So for that, the best way to do would be to look at the linear part. I take a point x0. I look at the point x0, u of x0 on the graph of u. Then I look at the tangent plane here. I use the purple color to denote the tangent plane. And then I lift the tangent plane by an amount h up. H I think is tiny. And then I hope that when I cut with the tangent plane after I lift h up the graph of u, I will get something that is compactly including the domain omega, and I'm in the situation which I can apply the estimates. So this is very important. So provided, this is called the section of h centered at x0, this set obtained by slicing the graph of u by the tangent plane at x0 at height h and looking at the domain below this this lifting of the tangent plane. And this is called the section at x0 of height h, and has the same property as Euclidean balls when we deal with the Laplace equation. These are the correct sets to write estimates on. So for Laplace equation, we try to write an estimate. We go from the unit ball to have the ball. For the Monge-Ampère equation, we try to use sections. So you can try to think h almost represents like the radius and x0 the center. Yeah. On the other hand, these sections depend on the solution itself. Yeah, as I change the solution, the sections, they just follow the solution. Yeah. Something that doesn't happen, of course, with the Laplace equation. I mean, the domains that are fixed here, they are moving. Okay, so the key assumption is every time I take such a section for some tiny h, and as long as this would be compactly including omega, so as long as the section would close fully inside of omega, and I get that u is equal to 0, then, and I solve a determinant of this curve equal to f, then I can say that u is very nice. If f is smooth, u is smooth. Yeah, so I get all the regularity I want from Pogorelov estimate. Okay. So, okay, now what we discussed also last time is that when I have such a section, I mean, I denoted here, drawn here with green, we want to do an affine deformation to it, and we can make it round. And this is, last time we discussed John's lemma, that if we have any bounded convex set K, then there is an ellipsoid that approximates it, in the sense that there is some point x0 inside the convex set K, such that x0 plus E is included in K, but x0 plus a dilation of E, n times E, includes the set. So we say that the set K is equivalent, or let's say has the shape of an ellipsoid E, of the ellipsoid E. So when it has the shape, means that it's comparable in this sense given by John's lemma. And with this, essentially says that you give me any such section of a solution to the Monge-Ampère equation U, I can always make that section look round. What do I need to do? So I need to subtract the linear part plus h here. I need to scale space by a linear function ax. Yeah. Then I have to multiply with some scalar in front of everything. In the case when a is just with determinant 1, I don't need the first part. But in the case when a would be a dilation, I need also to rescale the function itself, yeah, to preserve the right-hand side. So the natural rescaling would be given here, that u tilde of x would be u minus l scaled by x, but corrected by the determinant of a to the power minus 2 over n. And then the right-hand side scales just by the affine transformation AX, by the linear transformation AX. And then I have a new solution, U tilde, that solves more or less the same thing. If I think that F tilde was 1, that was constant, I would still solve the same equation. But the only thing that I did is that the set where U is less than 0 now is comparable to B1. So the picture of such a solution U tilde, which would be a renormalization of U, is shown on the right, in which I have a ball, a unit ball inside the domain. My domain is included in the ball of radius n. And in here, U is equal to 0 on the boundary of this. This would be a section that I call S tilde. And on the boundary, I solve on inside, I solve the determinant of this square of U tilde is F tilde. Okay, now let's see. So what this we discussed last time, what I want to start talking today is about Cafarelli's interior regularity theory for the Monge-Ampère equation. And this would be estimates like C1 alpha and C2 alpha estimates, some sort of Schauder theory for the Monge-Ampère equation. And then I'll give some application of this theory to some problems. So let's discuss Cafarelli's approach. And the main idea is to say that actually after renormalizations, all the solutions, they are in fact form a compact family. So Cafarelli noticed that, well, let's set ourselves up in the setting in which the determinant of this curve is f, and our right-hand side f is bounded between two constants. Let's think bounded between 2 and 1/2, or I don't know, 100, 1 over 100. Yeah. This class of equation remains invariant under the transformation that I said previously, because our f is just reshuffled by the linear function a, but we cannot, if the original f was between two values, also the rescaled f would be between the same two values. Yeah. Okay, so Cafarelli noticed that this family of solution is in fact compact. Okay, so let's discuss what happens. So if we start with the general solution U, and we take a section H centered at x0, as we talked in the previous section, on the previous page, we can renormalize this into a U tilde and the section S tilde of H tilde, but this new, the rescaled section is comparable to B1, like in the picture here. Yeah. So what we claim here is that the height of the rescaled function is comparable to 1. Yeah. So this is what I want to convince you, and also that the minimum occurs at the origin. I rescaled x0 to move at the origin, right? And the minimum that occurs at the origin cannot be too close to the boundary of the corresponding section of U tilde. So this tells you, in fact, that this function U tilde is very rigid. Yeah, I mean, its height is sort of order 1, and its minimum cannot occur too close to the boundary. Okay, so let me convince you of this claim. So this follows by, let's say, why is the height meaning the minimum value of U, why is the minimum value of U that you go below 0, right? The absolute value of how much your function drops below 0. Why is it comparable to 1? Well, this just follows simply by the maximum principle. I know that inside the domain, I have a ball drawn here with red of radius 1. Yeah, so that is inside the domain. And then if I can build an explicit quadratic polynomial V that vanishes on the boundary of this ball of radius 1, for which the determinant of V is very tiny. Yeah, so this means that I just have to take a quadratic polynomial that just bends a little bit down. Yeah, I mean, it's almost flat, but it bends a little bit down. I can make the determinant be less than capital lambda to the -1. Sorry. So here I have capital lambda to the -1. Then by maximum principle, the red function has to stay above the solution U by maximum principle, or by the definition of viscosity solutions. Similarly, I know that there is a large ball drawn with, I mean, here I use the color orange, that includes a domain where U is 0. Then I can build a solution, an orange solution W, still a quadratic polynomial where the determinant is huge. And that would need to stay below U. So I trap U between these explicit functions. And that tells me that the amount that U drops below 0 is indeed comparable to 1. Yeah. Why is so this is one of the two claims. The second claim is that this minimum point where the minimum occurs cannot occur too close to the boundary, like drawn here. So on the bottom, I'm trying to convince you that the picture cannot look like this, that I have a solution, not a solution, I have a function U tilde that satisfies star, that the determinant is bounded by above and below, but its minimum is very, very close to the boundary. This is like a standard argument. This is like Alexandrov argument. So the fact that the determinant of this curve of U tilde is bounded between two constants, small lambda and capital lambda, in terms of the gradient map or the subgradient map, it says that if you give me any set D, if I look at the image of the subgradients of U on the set D, then it's measured, is Lebesgue measure of all the slopes, supported on D, should be proportional to D, to the measure of D. Yeah. Now, what happens if the minimum occurs very close to the boundary? You can say like this, let's look at all the supporting planes in the whole section S tilde, right? So I look whatever is drawn here. So I look at the blue function and I look at all its supporting planes. And the top line tells me that the supporting plane should have measure of order 1, because S tilde has volume of order 1. On the other hand, the total slopes that are tangent to S tilde include, so I'm going to draw a cone from the minimum point of view, like the red cone here, that connects the minimum point of view with its 0 set. Yeah, that I call that cone C. Yeah, C is the red cone. So all the supporting planes to C at the origin, they are also supporting planes for U in SH. Yeah, if I take any plane, any red, or let's try any purple. If I take any purple plane that is supporting to C at the origin, I think that if I take it down to negative infinity and I lift it up, it's going to touch the blue graph at an interior point. So that tells me, in fact, that the measure of all the slopes of the gradients in S tilde is going to be bigger than the supporting slopes of the cone C at the origin. But this set is very large if the minimum is very close to the boundary. Why is that? Is because in some direction here, in the direction in which I'm very close to the boundary, I have very large slopes. Yeah. So the image, the gradient of this cone is a convex set. Is a convex set. It's easy to show that this is a convex set. On the other hand, if I'm very close to this point, to the boundary, then I contain this convex set contains a point very far away from the origin, and also contains a ball around the origin, and I contradict. So this would be very large. So let's say this would be very large if minimum, if 0 is too close to the boundary. To the boundary of S. So at the end of the day, what this shows, it shows you that indeed after rescaling, your picture is going to look exactly like I draw it, like this, that the minimum cannot be too close to the boundary, and this thing is of order 1, and everything is of order 1 after rescaling. In particular, I can use, for example, what I want to emphasize here, the fact that the minimum is not too close to the boundary means that I can take a tiny ball around the minimum point and multiply that maybe by 100 times around it. And S tilde would be contained between these two balls. Yeah. I already knew that S tilde is contained between two balls, a ball of radius 1 and a ball of radius n, but I didn't know what the center of those two balls were. Once I proved that the minimum point is not too close to the boundary, I can think that actually those two balls, I can take them to be centered at x0 as long as I'm allowed to give up a factor. Yeah. So at the minimum point x0, I can try to think that I have a ball of radius 1 over 100, and everything is included in the ball of radius 100. Okay, so at the end of the day, the rescaling I'm going to do it one more time. I mean, this argument, whatever I said, that the minimum doesn't occur too close to the boundary, and the height is of order 1, says the following thing. So I'll write one more time the rescaling slightly different. So we assume we have a solution U that solves the determinant of d square of U is bounded between small lambda and capital lambda. And I assume I know these two constants, small lambda and capital lambda, and all my other constants will depend on them as well. Yeah, so these are known, and all the estimates depend on small lambda and capital. I'm assuming that the section at height h at x0 is compactly included in omega. Then there is this rescaling. I can find an affine deformation of determinant 1, so really measure preserving, right? Such that when I look how the section of height h at x0 looks around x0, right? It looks like an ellipsoid EH. I can put an ellipsoid EH that is drawn with green on the bottom. Yeah, so x0 you can try to think is the section here. X0 on the bottom here is the center of the section. SH of x0 is the convex set, is the section. So I can find an ellipsoid E sub h that can be written as a tiny constant, universal constant C0 times AHB1 multiplied with h to the 1/2. Yeah. This ellipsoid EH is included in SH of x0 minus x0, and the big multiple of EH, C0 prime EH, contains this. So it's exactly the same as John's lemma, except that these ellipsoids now are centered at x0, and I know that their volume are precisely, so I know the volume of EH. Let me write it here. In green is that the volume of EH is like h to the n over 2. So they are essentially like balls of radius h to the 1/2 that are deformed by a measure preserving transformation. Okay, so this is the rescaling U tilde, and at the end of the day, to understand really what happens to second derivatives of u at x0, you really need to understand the shape of this ellipsoid, this sub h. Yeah? So, for example, if I let me do here a tiny example on the right, and say if your function u, let's take a particular solution, u0 would be 1/2 x squared. This is like the most basic solution to determinant of d squared of u0 is 1. Yeah? So this is just the quadratic polynomial. Yeah? If I look at the sections at height h, what I'm going to get here, I'm going to get like a ball of radius h to the 1/2. Maybe there is a square root of 2 in front of it, but we don't care so much about. So the sections here look like round balls. It doesn't matter how small h is, the smaller I take h, the section will still be round. Yeah, they have the correct volume, sort of the volume is always the same, but they look round. On the other hand, if I do an affine deformation to this, if instead of the polynomial 1/2 x squared, I make 1 over delta x1 squared plus delta x2 squared, 1/2 in front of everything. It's like this picture that is stretched much more in the x2 variable and contracted in the x1 variable. So while the volume of the sections remain the same, their eccentricity, by eccentricity we mean the ratio between the longest axis of EH divided by the smallest axis of EH. So the volume is the same, but the eccentricity of EH encodes the behavior of the second derivatives. Yeah? So the second derivatives at the point x0 is encoded in the shape of this SH as h tends to 0. As long as they remain round, means that the second derivatives remain bounded. As long as they start stretching in some direction more and more and more, means the second derivatives are blowing up. Okay. Okay, so now let's talk about structure of the set of singularities. So for the Monge-Ampère equation. So as long as a function, as long as I take a point on the graph of u, and as long as I take a point x0 that my function is strictly convex at x0, I know that I can lift up a little bit the tangent plane and have a nice section that closes inside the domain. The question is, at what points can I do this? Which one is the set of strict convexity? So somehow the set of strict convexity is associated with the set of regularity. So I want to check at what points the function is not really strictly convex. So let's pick a solution u with a bounded right-hand side, and look at the point where u of 0 equal to 0, and I assume that the tangent plane at the origin is 0. Yeah? So u is greater than or equal to 0 everywhere. I would like to understand how big or what is the shape of the set where u coincides with this tangent plane. Yeah? So there is this claim that the set where u coincides with the tangent plane is, of course, is a convex set, but it's only supported on the boundary of omega. It has to exit the domain. what does it mean, right? So it means somehow that the set where U coincides with this tangent plane has to exit the domain, cannot finish inside the domain. If I have a segment, let's say if I see a segment where my function U coincides with the plane, and I mean, I don't know, then sort of this segment will have to exit the domain. Yeah, I mean, so the set where U is 0 has to be supported on the boundary of the domain. Okay, so let's see why this is the case. So I draw here a picture on the right in which I assume that the 0 set is in fact looks convex like this on the bottom. So this is the 0 set of U with blue here. And then imagine that the graph of U lifts up, but I have a boundary point sort of the 0 set has an extremal interior point that I call that the origin. Well, if that is the case, then you can, instead of using 0 as a cutting plane, right? So you say, well, at the origin, I want to use, I want to lift a bit the tangent plane. The tangent plane would be 0. And I want to look at the set where U is less than 0. Well, you don't know if that is compactly included in the domain, but what you can use instead, you can use some sort of plane like tilted a little bit to the right. If the picture looks like whatever I draw on here, then I want to use not the plane xn equal to epsilon, but rather I want to use a plane like epsilon times xn plus delta. Yeah, so this means that from the origin, I'm going back in the xn direction at distance delta. Let me draw it here with red. So I'm going delta backwards. And then I lift a little bit the plane, like the purple plane up, and I'm trying to cut the graph of U. Yeah. So when you cut the graph of U, you get some lengths there, right? Drawn with purple. So if I want to look at this picture by above, I'm going to see the 0 set like this. And the purple set would be here like this, and then like this. This would be the purple set when I look at the picture by above. But as epsilon tends to 0, the purple set converges to the blue set. Yeah. So as the epsilon, as the slope of the purple plane tends to 0, the purple picture goes to the blue picture. On the other hand, the origin is very close to being a minimum if I look at U minus this linear function. So let's call this purple linear function, let's call it L. And I'm looking at U minus L. That would be 0 on the boundary of the purple region. But also its minimum point of U minus L, I mean 0, the origin is very close. Let's say the value of U minus L at 0 is comparable of the minimum with the value of the minimum of U minus L. And this is sort of geometrically clear that when I look at U minus L at 0, I'm very close to being minimal, up to an order, I don't know, up to a factor of 2. So this tells me, in fact, that my section has to be balanced around 0. Yeah, it's like, this means that around 0, I should always be able to put an ellipsoid inside and an ellipsoid outside with radius centered at the origin, with the ratio between them being a given constant. And that's clearly not the case, because as the purple region converges to the blue region, the origin gets closer and closer to the boundary of the domain. Yeah. So somehow what you contradict here, you contradict that the set where U is less than L, U less than L should be balanced around 0. I mean, you can think essentially this is like a section at 0. It's slightly different than a section because I tilted a little bit the tangent plane, but morally still a section at 0. On the other hand, 0 is too close to the boundary. after rescaling. Yeah. Okay. Okay, so what did, yeah, so in some sense what this says, it says that if I have if my function u coincides with the tangent plane, then actually this region has to be supported, has to exit the domain. Okay, how do we use this to prove, so this can be quantified to prove C1 alpha estimates. Just this simple simple observation. Yeah? How do we quantify it? So think about that we have a normalized solution, meaning that the section at height 1 at the origin being the minimum point, is comparable to B1, like in this picture here. Determine this in between two values. Then what I would like to say, I would like to say that this function has to be strictly convex inside. Is it strictly convex inside? Sure, because the set where u coincides with this tangent plane has to be supported on the boundary. So, but u is already 0 on the boundary, right? So any convex set that is supported, I mean, here I cannot have, let's say if I look at the set where u coincides with the tangent plane at x0, yeah, this would need to be supported on the boundary. Is not possible because the function on the boundary is 0 everywhere, yeah, and u inside the domain is less than 0. Yeah, this tells you that u has to be strictly convex. So the previous argument tells you that u has to be strictly convex. The fact that u has to be strictly convex can be okay, but how strictly convex has to be uniform, because this is a compact family. So if you are managed to prove that each element is strictly convex, in fact, you get a uniform modulus of strict convexity by compactness, because all this family, if I take a sequence of elements in this family of normalized solutions, they converge to another normalized solution. Yeah? So whatever you can say from for any element, it can be made uniform for all of them by compactness. So the fact that u is strictly convex inside this section can be said quantifiable in the following sense. If I take the cone generated by 0, my minimum point, and the section S1 that I draw here with red, so you think I have a red cone generated by the section at height 1 and its boundary, yeah? And I draw the red cone, and then I'm cutting the red cone in my solution at level 1/2. Yeah. Then what I get here with blue, this would be the section at height 1/2 at the origin. Yeah. But this section, just because my function has to stay away from from the red cone, this would be, so written here, S1/2 of 0 would have to include 1/2 plus delta S1 of 0. So if I just put here delta, if I just say 1/2 S1 of 0, that would be exactly the red set. So if I wouldn't have any delta there, if I wouldn't have this delta here, this is just convexity. This is some obvious statement. The fact that I have a delta tells me, in fact, that my next section at the next level has to become slightly bigger than what the cone would do. And how much bigger, I'll draw it with red, has to improve by a fixed ratio, right? So this delta somehow says that if I look at the cone at height 1, and if I look at the cone at generated, so this is generated by S1, and if I look at cone generated by S1/2, there is an inequality between them. I said that 1 minus delta of this is bigger than or equal than that. Yeah. So every time I slice the graph halfway, the cones, these cones have to open up a fixed amount, a fixed amount, a fixed amount. As I zoom in and I keep on cutting, it says, in fact, that these cones have to open more and more and more and more and more. And this is, in fact, a C1 alpha estimate. It says that the tangent plane has to be zero at 0, but also with some modulus of continuity. So this estimate iterated, this one implies C1 alpha estimates. So C1 alpha estimate, like essentially what it quantifies, it's a quantified version of the strict convexity of solutions and compactness. So this is Cafarelli's argument, and at the end of the day, let me write here the theorem. These are the, so we are in the setting the determinant of U is equal to F, and the right hand side F is bounded by above and below from 0 and infinity. Yeah. And let's say if I take a normalized solution, then I can always say that its C1 alpha norm is uniformly bounded. And the alpha here just depends, alpha here depends on the dimensions small lambda and capital lambda. The more this constant small lambda and capital lambda degenerate to 0 and infinity, the least the alpha is. All my estimates sort of become worse and worse. But once you fix a small lambda and capital lambda, you can say that U, any solution U, is C1 alpha in the interior. So this is just a little bit of an improvement. A convex function in the interior is already Lipschitz. So sort of the fact that I'm dealing with convex function is very good, is Lipschitz. What this says is it improves a little bit. It just gives an extra, like you go from Lipschitz to C1 alpha for some tiny alpha. But then this can be iterated. So I'm not going to insist what Cafarelli, this is the key step, I would say, theorem 1, to understand that you can go from Lipschitz to C1 alpha and to localize things. And essentially, if in addition, you know that F, instead of just being bounded, if it's Holder continuous, then you can prove that your solution are in fact C2 alpha. And these are like Schauder estimates. So, an intermediate step between F being C alpha and F being bounded, if F is just continuous, then you can prove that U is W2P for any P. So this would say that it's almost C1, it's almost has bounded second derivatives, not quite, but almost. So this is very similar to what happens to Laplace equation, right? If you give me a right hand side that is just continuous, you are not able to say that the second derivatives are bounded, but almost bound. So I would say theorem 1, 2, and 3, this is what people refer to Cafarelli's interior regularity theory for the Monge-Ampère equation. Of course, it's all you need first to get sort of this section SH at x0 to be completely including omega. This is the starting point. Then you can normalize and get all these uniform estimates after normalization. Okay, so now let's do some, why do we care about these things? So let's talk about some applications of these theorems. So one application is the Minkowski problem that I mentioned in the first lecture. So the Minkowski problem, you're looking for a convex set K in which you prescribe the Gauss curvature of K in terms of the normal and the position. So locally, you think locally, if you give me a point, so I denote the boundary of K locally as a graph x u of x, and denote the points as capital X on the boundary of K. And I pick a point capital X0 here on the boundary of K. And locally, the Minkowski problem, well, the existence in the Minkowski problem can be done using Perron's method and so on. So you say, well, I have a solution which is weak. Weak meaning that I know some things, but just in, let's say, viscosity sense or in the Alexandrov sense. Yeah, how do I prove, in fact, that I have a classical solution? So when you write the Minkowski problem for a graph, it reduces to saying that I have the determinant of this square of u is equal to a right-hand side, but my right-hand side depends on the position, which is xu. Xu is the position where I am, but also on the normal. So it depends also on the gradient of u. So how do I apply the theory? I mean, this f is bounded as long as the gradient does not degenerate. Yeah. So the way to argue would be the following. Let's take a point x0 and let's assume at the beginning, let's assume that the boundary of k is strictly convex at x0. Yeah, so I draw the tangent plane at x0, the boundary of k. And if the boundary of k is strictly convex at x0, I can lift up a little bit this tangent plane and try to cut a slight piece of the boundary of k and try to see what do I satisfy there. And over there, because I cut a very small length that is closer and closer and closer to x0, over there, the function would be Lipschitz. Yeah, if I take a very tiny region around x0, the fact that I have a ball inside the domain, inside the set k, guarantees me that in a very tiny region around x0, my graph of u is Lipschitz. When I write in terms of, let's say, the vertical, with respect to the vertical direction. So all you know is, in some sense, that you satisfy an equation like this, but the gradient of u is just bounded. Yeah, which means that your right-hand side to start with, you only know is just that it's just bound in a tiny region around x0. However, that's enough to start to apply theorem 1, because in theorem 1 we just want a bounded right-hand side, and then we can say that actually our solution gets better. So the fact that the gradient of u is in L infinity near x0, yeah, and this is a section. I mean, I'm working in a section, and I solve some sort of equation with bounded right-hand side. It allows me to say that actually u is better than Lipschitz. U is just C1 alpha. The gradient is in fact Holder continuous. But then I go back to the equation and say, well, actually, once the gradient is Holder continuous, my f is not only bounded, but is Holder continuous itself. So then I can iterate. The fact that f is C alpha, then I can apply the C2 alpha estimates and say, well, u is C2 alpha. And then once u is C2 alpha, you're basically back to linear theory, and you can bootstrap this as many times as you want. But this argument essentially says how you start from just a bounded right-hand side, you improve a little bit on u, the fact that the gradient improves, and that allows you to bootstrap and iterate more and more and more. So this argument, holds at the point of strict convexity, but who tells you that points are really of strict convexity? For example, here on the bottom, think that you're set. I mean, let's exaggerate the picture and think that you are in 2D and your boundary of k is a triangle. Yeah, if you take a point x0 and you try to cut the length around x0 with a plane, you can never do it making it a graph in the vertical direction. Yeah. So the argument on top can be applied at points of strict convexity. Well, actually, it can be applied at points slightly more than strict convexity. They can be applied at points that are extremal for the boundary of k. What is an extremal point for the boundary of k? One that I can cut with the plane and get a region that converges to a point. So a point is extremal. Like I'm saying that a point is extremal to a convex set. Let me draw here a picture. So, okay, so a point is extremal of a convex set if I can find planes that I can slice the convex set closer and closer and closer, and I can make lenses that converge to that point. Yeah, so this would be an extremal point, and the argument that I said initially I can always apply it, because all I used is that I have tiny sets where my function is Lipschitz, and I can apply the theory of the Monge-Ampère equation. But on the other hand, if the boundary of K is strictly convex at all extremal points, it turns out that the boundary of K is strictly convex everywhere, and the argument on top can be applied at all points. So basically, on the picture of the triangle, you say in the following sense: let's say that my boundary of K is not uniformly convex, it takes 0. Then what I do, I take a straight piece of line at x0 and I follow it till I reach an extremal point. Yeah. And at this extremal point, x1, I say, well, this is an extremal point. Near x1, I can apply the arguments, and again, my function is C1 alpha, but not only that it's C1 alpha, but it's strictly convex. And I contradict that it's strictly convex because this point, I knew that there was a whole segment that connected x0 with x1, therefore it cannot be strictly convex around x1, uniformly convex around x1. Yeah, so this argument shows that, so this argument shows how to apply this theory to the Minkowski problem. Another one, a similar argument can be applied to show that the only global solution to the Monge-Ampère equation, are quadratic polynomial. So if one looks for a global solution, determinant of this curve equal to 1 in Rn, then it turns out that U has to be a quadratic polynomial. Why is that? Well, okay, so let's do like a quick proof. Let's assume for simplicity that U is 0 at the origin and gradient of U at the origin is 0. You can always assume this after subtracting a linear function. So what you want to show first is that U is strictly convex. Yeah, it's very important to get this strict convexity to start talking about sections. We already know that if U is not strictly convex, then the set where U coincides with the tangent plane, in other words, U equal to 0, needs to have U has to be supported on the boundary of the domain. Well, now because we have a global solution, U equal to 0 support on the boundary of the domain is infinity. So the only case that you have to rule out is that there is a straight line that goes through the origin from negative infinity to infinity where U is equal to 0. So this is what you have to rule out. Is it possible that I have a solution to determinant of this curve equal to 1 that contains a straight line that extends everywhere? It's more or less like Pogorelov example. But Pogorelov example, as I said, is always cannot be extended to larger and larger domain. But if you assume that you have such a solution that goes from negative infinity to infinity, well, it's a simple exercise to say that actually your function U needs to be constant in that direction. If somebody tells you that along the x, that U of t 0, 0, 0, 0, 0 is equal to 0 for all t, then actually U has to be constant in the x1 variable by convexity. And if you have a solution that is constant in one variable, clearly cannot solve the equation because the gradient map maps Rn into a lower dimensional space. And that's not possible. So the most important part would be this that we just talked about, that U is strictly convex. And it all comes down from the argument that we did that the set of singularities has to be supported on the boundary of omega. All these things are consequences of that argument. After the fact that U is strictly convex, after we prove that U is strictly convex, then we start looking at sections, but now we take sections with h tending to infinity. So we start cutting the graph of U at heights higher and higher and higher that go to infinity. Yeah. And one claim is that these sections, the eccentricity of these sections at infinity, they are related to the eccentricity of the section at height 1. So there is a relationship between eccentricity, eccentricity meaning how long, how stretched the sections are. If they are very stretched at infinity in one direction, then they have to be also at unit scale, they have to be very stretched in that direction as well. And this follows from Pogorelov's C2 estimate. Why is that? After rescaling, you can try to think that the section at infinity in the rescaled picture is the section as height 1. Yeah. And you solve the determinant of this square of U equal to 1 inside here. Now, Pogorelov estimate says actually you have C2 estimates near the origin. Having C2 estimates near the origin says that actually the sections very close to the origin, they have bounded eccentricity. So their eccentricity here is the same as the eccentricity of S1, yeah? Which in reality says that the eccentricity between any two sections, one that tends to infinity and the one at size 1, they are comparable. And Pogorelov estimate, in fact, says a little bit more. Says that if I look closer and closer and closer to the origin, my sections start looking more and more and more like exact ellipsoids, because my function U here is closer and closer and closer to a quadratic. When you unravel this, it says that the section at size 1, right? This is in the blow down picture. Yeah. In the original picture, it says that the section at height 1 has to be an ellipsoid. So it says, in fact, that your function has to be a quadratic polynomial. So Calabi's theorem essentially follows from Pogorelov's C2 estimate plus some strict convexity argument. Okay, I think, do I still have 5 minutes or I'm pretty much done?
Yeah, you have about 5 minutes.
Okay. So the third application, well, maybe I don't have a lot of time now, but the third application is about optimal transport. But maybe I'll spend more time next time on this. But just to mention, the optimal transport problem, we try to map a density f of x dx into g of y dy. We have two probability densities, and we have a cost function of transporting points. So let me, at the beginning, consider the quadratic cost, which is x minus y squared. And then the optimal transport problem says I want to transport the x variable into the y variable by a measure preserving map. So I want to preserve measure, but also to minimize the cost. And the total cost would be given by x minus y squared relative to the measure, right? Relative to f of x dx. And there is this theorem of Brenier that says that there exists, I'll explain it next time, maybe, the theorem of Brenier, but there is a convex function so that this map is in fact the gradient, or if you want, the subgradient of a convex function. Yeah. Then, at least formally, this U, the fact that I transport the x measure into the y measure by a measure preserving map, it turns out that U needs to satisfy again a Monge-Ampère equation in which the right hand side depends on the gradient of the function itself, right? So again, I can try to argue as before, if f over g is bounded, and I can prove that U is C1 alpha and says something about the optimal transport map. Yeah, so the optimal transport map is the gradient. Okay, However, there is a catch here because it's not clear. I mean, I saw the Monge-Ampère equation at the points where I expect my map to be nice and to be differentiable. I don't know that ahead of time. So actually, next time, now I don't have the time, but next time I want to go a little bit through the not main state, but I would say to give an overview of why there is such a convex function U, and in which sense do we really satisfy this equation here. Yeah. Determinant of this square f equal to f of x divided by g of the gradient of U, and apply this theory, this Cafarelli interior theory, to the optimal transform map. But I will stop here because I don't have time at this point to go into more details. So